Now again, that's 205. That's a review. That's not what we're about here. In 207, we're doing this. A mass bobbing up and down on a spring. And we call that simple harmonic motion. The most important word there is simple. And I'll explain to you in a little bit why it's simple. Now we can characterize simple harmonic motion by the timing of the motion. We can do that two ways. We can either talk about the period, the time it takes to make one oscillation, one down and back up, or we can talk about the frequency, how many times it makes oscillations per unit of time, per second. Okay? This motion in terms of the amplitude. And we define the amplitude as the furthest distance that this thing gets away from equilibrium. How far does it get away from its happy spot, where it would just rest forever and not move? Can I just pause a moment and ask, how many of you right now deeply care about masses bobbing on a spring? That's just something you've always been dying to know about? You'll notice that my hand's not up either. Okay? No one in the room cares about masses on springs bobbing up and down. So why am I forcing you to learn about that? Well, it turns out that if you put on your magic glasses that can see microscopically, things that seem solid really are made up of a lattice work. And if you look at that lattice work, it behaves very, very much like masses representing the atoms and molecules in a lattice with their neighbors, connected by forces that can be represented by the springs. These forces happen to be electrical, but in practice, it looks like a whole bunch of masses connected by a whole bunch of springs. And so it turns out that if you understand this problem, you understand the world around you. Now, I did not fully understand that concept. I did not fully appreciate it until I got to MIT. Now, MIT accepts graduate students from all over the world. Every country in the world sends their geekiest people to MIT. And all of those different places have different grading systems. And so they're not really sure that everyone belongs there. And so the first thing you do when you get off the bus is you take a 5-hour qualifying exam. And that qualifying exam is to see whether you really belong there or whether you need to get back on the bus and go home. Now, I knew in my heart of hearts that I didn't belong there. I knew that everyone there was smarter than me. I knew I was going to fail this exam and get back on the bus. When they gave me the exam, the first question on the exam was this motor, a heavy motor that was turning. The motor was sitting on a thick rubber mat. And as you changed the rotation speed, you found a particular speed at which this motor bounced up and down at the largest amplitude. Now that was it. At that point, I just panicked. I had never in my undergraduate studies encountered a problem anywhere remotely similar to that. And I knew I was going home. And I sat there and I just stared at that problem for the longest time, wondering how I would tell my wife that we were packing again. And then I realized that the motor was going up and down, up and down, up and down. Simple harmonic motion. I realized that the mass of the motor was the same as the mass of this block. And the rubber pad, the rubber mat, was acting like the spring. And they gave me enough information about the mat to figure out the spring constant of the spring. And suddenly, it became a mass on a spring. And I solved that problem and I turned the page, and dang if it wasn't another mass on a spring problem just dressed up as something else. I kept solving that same stupid problem over and over again, and I got to stay at MIT, and that's why I have the job I have today. You may not care about this problem, but I think it's the most important problem in the world. It allows me to teach you. It allows me to come and work with you. Okay, let's start simple. You got a block on a spring that bounces up and down every 0.25 seconds. How many times can it bounce up and down in 1 second? It's not rocket science. 4. Yeah, all you did is take 1 over 0.25. Okay, if the period is 0.25 seconds, you can fit 4 of those into a second. Okay, so the frequency is 4 oscillations per second, and we give that the name Hertz, Hz. That's just to honor a dead professor, the most noble thing you can do with your life. Okay? Now, you can see that the period is just the inverse or the reciprocal of the frequency and vice versa. That the frequency is 1 over the period and the period is 1 over the frequency. Okay? So if you know one, you know the other. Now, this is an old exam question, a simple question. We're going to use our clicker to answer it. What is the frequency of the second hand on a clock? And we're assuming an analog clock, not a digital clock. The frequency is just number of cycles or repetitions per second. Well, a second hand goes around every minute, every 60 seconds. And so if I want to know how many cycles happen in a second, I divide 60 into 1, and I get 1/60th of a hertz. Okay? Now, what if I want to change the period of the motion? What if I want to increase the period? I'm going to keep the same spring, but I'm going to change the mass. Should I reach for a smaller mass or a bigger mass to increase the period? Talk to your neighbor. Which would it be? Which of those? Okay. Think about what I'm asking. If I increase the period, am I making this thing move faster or slower? Shout it out. Slower. So to make it move slower, I'm going to want the larger mass because it's harder to speed up and slow down. It has more inertia. Whoa, whoa, whoa. Like trying to move a football player. Okay? If I put a smaller mass on there, doink, 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 doink. Okay. Now, what if I had asked you what you want to do if you want to increase the frequency? Am I making it move faster or slower now? Faster. So I would decrease the mass. Decrease the mass. Okay. Now, this is a very, very simple exercise just to make sure that we're all on the same page. There's 2 flavors of this problem. There's the problem where the mass bounces up and down on a spring. There's the easier situation where it bounces left and right. Now, folks, when we do these problems, we have to slide on something. And we're always, always, always in this class going to slide on the frictionless table. Where do we get those frictionless tables? In the basement of the physics building. Okay? Now, if you put friction into this problem, it becomes a very rich problem, a very important problem for everyday life. We deal with this problem in the Physics 301 class that's taken by our physics majors. You solve it with a differential equation. It's a very fun problem. But in our case, we're always going to take the frictionless table, and so this block is just going to bounce back and forth, back and forth, back and forth between this turning point and this turning point. I've shown you the positions where it stopped to turn around and go the other way. Now, with your clicker, tell me what the amplitude is. Okay. Last call. If we all get this right, I take you all to Mexico. Okay. The most common answer is B, which is 0.5 meters. That is not the correct answer. That is not the correct answer. You remember, we defined amplitude as the biggest distance, the greatest distance it gets away from equilibrium. Well, what's equilibrium? Equilibrium is where the forces are balanced. In this case, the weight force is always going to be balanced by the normal force by the floor, the table. So we're looking for a place where that force by the spring is zero. Well, when the spring is compressed, it's pushing to your right. When the spring is stretched, it's pulling to your left. The only place where the spring is neither pushing nor pulling is right in the middle, between the two turning points. At that point, the spring is just exactly the length it was when it came out of the box from the factory. Okay? Now, the biggest distance it gets away from that equilibrium point is 0.25 meters, and that's the amplitude, is 0.25 meters. So very few of us got that right. Okay? And I'm not going to take those few to Mexico because that'd be expensive. Okay.